We got a picture here of a trough 10 feet long. The ends are isosceles triangles. It has an altitude or height of 3 feet and a base of 4 feet. And the vertices are at the bottom. Water is being poured into the trough at a rate of 3 cubic feet per minute. How fast is the water level rising when the water is 1 foot deep? So first of all, in a related rate question, we have to analyze what's changing. Volume is changing with respect to time, and height is changing with respect to time. So is the width and the slant heights. There's a lot of things changing, but we're wanting to find dH dt, and we're given dV dt. So what we're going to want to do is we're going to want to make an equation with volume and height. Since we know dV dt, we could use that to find dH dt. And we want to find it at the specific moment the height is 1 foot. So the interesting thing here is when we go to get the volume formula, though, volume of a triangular prism is the area of its base times its length. We know the length is 10, and the base is a triangle, so that's base times height divided by 2. But we have a little problem here. We have another variable we haven't accounted for. We've got the variable b. So we need to somehow rearrange this formula so that it's only in terms of h. And that's the beautiful thing about triangles, is that this triangle here is similar to this triangle here. So ratios of sides are going to stay the same. What do we know? We know that the base divided by the height is 4 over 3 for the big triangle. That ratio has to stay the same no matter how big or how small that triangle is. This allows me to rearrange for b and get b by itself, and I know that the base is always going to be 4/3 of the height. And I can substitute that in to my formula. So I took the 10 divided by 2, I got the 5. 5 times base times height, and now I substituted my base for 4/3 h, and I have created an equation for volume that's just in terms of height. I can now do implicit differentiation on both sides with respect to time. The derivative of volume is 1 dV dt. The derivative of 20h squared over 3 will be, bring the 2 out in front, 40h over 3, and then times dH dt. And then it's just a matter of, we wanted to solve it when the height was 1, so you plug in 1, we plug in 3 for dV dt. Type this into our calculator or leave it as a fraction. 0.225 feet per minute. Okay? So what do I see for you guys as the challenge in a question like this? This part with similar triangles. Having to take that ratio of the sides so that you could create a formula that was just volume and height. Technically, if you wanted to, you could have added, well, you know, it would be definitely tricky. You could add a dB dt, and you would have to figure out other ratios. No, it just would not be as much fun. Yes?
Can you scroll down, please?
Yeah. What also could be tricky in this unit is knowing formulas. Did you know the volume formula for a triangular prism? Any kind of prism, you do the area of the base times its height. In this case, it was on its side, so the area of the base times the length. Good? All right. So here is our Second question, this time we have a cone. The water tank is built in the shape of a circular cone with a height of 5 meters and a diameter of 6 meters at the top. Water is pumped into the tank at a rate of 1.6 meters cubed per minute. Find the rate at which the water level is rising when the water is 2 meters deep. So what are our two things that we're relating? We're relating height and we're relating volume. We know that dVdt was 1.6, and we wanted to solve for the rate at which the height is rising, dHdt, when h is 2. Do we have a volume of a cone formula? Yes. It is 1/3 of the cylinder, which is a circle times the height, pi r squared times the height. And we know we have a similar triangle here, right? This triangle with a ratio of 3/5 is going to have that same ratio when it's smaller. So we know the ratio of the radius over the height is 3/5. This allows us to get the r by itself, and you can plug that in. It makes sense to square this out so you can put your h's together, just so your derivative, when you take implicit differentiation, is easier. So I did the simplification, and now we can take the derivative with respect to time of both sides. So related rate problems. Setting it up is the tricky part. One, you have to know what you're relating. Two, you have to know a formula for what you're relating. And in this situation, we had to do a substitution using ratios of similar triangles. Once it's set up, the implicit differentiation is something you've done before. And usually they're just like, you're not going to get, none of the formulas of shapes that you know have like cosecant inverse in them, or any of those derivatives that you are slowly, I'm warning you right now, you are in the process of forgetting them. So, take time. Which are the ones you forget? Probably all the inverse ones. Those are the easiest ones to forget, because we learned them last, and you use them the least. Make sure that you take some time every once in a while to review. You know all 22 shortcuts. You will not forget the power rule very easily, because you will use it a lot. 3 comes out in front, subtract 1 from the exponent. dHdt. Now we wanted to solve for dHdt. We wanted to find it when the height was 2. We knew dVdt, and it's just a matter of plugging things in to find our value. Next type of problem are right-angle triangle problems. Two cars leave the same location at the same time. One travels due east at 60 kilometers per hour. The other due north at 45 kilometers per hour. How fast are they going away from each other after 2 hours? So there are three things that we're involving here. We know X is changing. We know Y is changing. We want to find Z is changing. How fast Z is changing. So we know dx dt is 60. We know dy dt is 45. We want to find dz dt exactly when the time is 2. Do you know any formulas with right-angled triangles? A squared plus b squared equals c squared. So we have this relationship that x squared plus y squared equals z squared. And if we take the derivative with respect to time of each of these, we get the following. 2x dx dt, 2y dy dt, 2z dz dt. And when we're thinking about this, we have to ask ourselves, okay, I know dx dt, I know dy dt, and I know that I want to find it when the time is 2 hours, but there's nowhere to plug in time here. How could I figure this out? Well, what would our triangle look like after 2 hours? Does it make sense that the one distance would be 90, the other distance would be 120, and if you did a squared plus b squared equals c squared, the z would be 150. So here's a question where we had to plug in the idea of time to make a specific triangle. We have a triangle that's changing, and we have a specific triangle at that moment. The time is 2 hours. This would allow me to plug in 120 for x, 90 for y, 150 for z. Plug those numbers in. Now, I'm going to get a little disappointed here. If I took 45 and 60, which were my original rates of change, and I do a squared plus b squared equals c squared with those, I get the answer right away. Triangles work that way. Right? If a squared plus b squared is the same all the way, doesn't matter how big or how small that triangle is, that rate of change will also stay the same. We could have just done a squared plus b squared equals c squared with our original amount to start with and got the right answer. It's nice to see, though, that our derivative rules work with 3 of them. In fact, we could take some time here to show why it wouldn't matter, and we could just do a squared plus b squared equals c squared right from the beginning. Okay. Just a quick mathematical way to show it. If I divided everything by 4, Do you see that this would be 60 times 60? This would be 45 times 45. And this would be 75 times something that I didn't know. Well, this is my a squared plus b squared equals, wonder what would have to go into the question mark to make the other side c squared. 75 again. Okay, so the right angle triangle ones, I mean, I feel like skipping this one. You could try this one on your own. For the video, I can show the answers, but we have another, it's like same kind of question. So I will just skip it. I'll put the answers up. If you want to practice it on your own, you can try it. But 1.5 squared plus 2 squared equals 2.5 squared. I don't know if you noticed these last two questions used versions of the 3, 4, 5 triangle. Like if you double everything here, 3, 4, 5. And the last one was the 3, 4, 5 triangle times by 15. Okay, so we're going to skip this one because it's exactly the same idea. But, ladders against houses. These are like, we in calculus love putting a ladder against the house. We can draw a picture of it. There's our ladder. There's our house. And you start going up the ladder and you realize you've made a fundamental mistake of not securing it. Or maybe you're using a ladder with wheels on the bottom. Also not very strategic. And as you start climbing the ladder, the bottom of the ladder starts moving away from the house, which means the top of the ladder starts going down. This is problematic. Could be dangerous. So what do we have? We have x is changing with respect to time, y is changing with respect to time. Do you see that z is always 20? Your ladder doesn't all of a sudden get bigger or smaller as it starts falling. It will stay constant. We know that dx dt is 2, and we want to find out how fast the how fast the top of the ladder is sliding down when x is 12. Well, we have a right-angled triangle here. So our relationship is set. X squared plus y squared. And this time we don't do z squared because we know that z is 20. It will stay at 20. Will be 20 squared then. And when we take the derivative with respect to time, we'll get our 2x dx dt, 2y dy dt, and the derivative of the 400 will just be 0. Because it's just a constant. Now, to fill things in, we have to think of the specific moment when the ladder is 12. Okay? So often we show two diagrams. Our first diagram here, shows the things that are changing. And then our second diagram is at the specific moment that we're wondering about. At that specific moment, the x is 12, the y would be 16, the hypotenuse would still stay 20. I sometimes see a danger for students. They take the specific moment, and then they do the derivative with a specific moment, get a bunch of zeros, and they're like, well, I don't know what went wrong. Okay? You're doing your equation with the general moment. And what's changing? We know that the y is going down, the x is going out. So we always show the variables that change as variables, because that's what a variable means, it changes. But once we've done our derivative with respect to time and we want to find a specific value, we want to find dy dt at x equals 12, well then we need to know what y is exactly at that point. It would be 16. And notice we get a negative answer here, because the x is increasing, but your y value is getting smaller, so it is decreasing. I think we have time for one more. And then we got an activity to get you ready for your first take-home quiz. So let's do one more. Because the right angle ones I don't think are too bad. The similar triangle questions, these can be a bit challenging. They're also a very favorite calculus style question. And we'll start with a picture of what's happening. You have a spotlight on the ground, shining towards a wall. The wall is 10 meters away. So I've got my wall with y. I've got 10 meters away there. And I've got a man who's 2 meters tall, perfectly exactly, because it would be a harder question if he was 1.83. So we'll keep it 2. He's walking towards the spotlight. How fast is his shadow on the wall decreasing? A man 2 meters walks from the... Oh, he's walking towards the wall. He's not walking towards the spotlight. He's walking towards the wall. So if you were walking towards the wall, spotlight behind you, your shadow would be getting smaller. And you're like, oh, I wonder when my shadow will be exactly the same height as me. And then you hit the wall. Not a good idea. Hopefully you stop before you hit the wall. So as the man is walking towards the wall, the y value is changing. So we have two things that are changing here. This value is going down. This value is getting bigger. The hard part in similar triangle questions is labeling. And you have some options in labeling. So a couple of things that you have options here. Where are you going to put your x? I could have put my x here, or I could have put my x on the left. Both of those values are changing. I chose this as my x because that is the value of 1.2 meters per second. If I choose this as my x, it's positive because it's getting bigger. We're going to find dy dt. It's getting smaller. We should get a negative answer in the end. Okay? I have both my, this is my general one. I'm going to just redraw it down here with my specific situation. Oops, I labeled them wrong. So we often draw one situation, which is our general, and then draw a second diagram which shows the specifics. We want to know when the man is 3 meters from the wall. This is our specific case. So now we're not going to use a squared plus b squared equals c squared, because the value that's changing x is on this triangle, and the value that's changing y is on this triangle. And those two triangles are similar. And if you have similar triangles, the ratios between their sides is going to be the same. So what I need to do is somehow set up an equation with those ratios, and my equation needs to include my x, because I know my dx dt is 1.2. It needs to include my y, because I want to find my dy dt. And then I've got my specifics where I drew triangle number 2 here with my specifics. How do I set this up? Well, if the ratios are the same, then 2 over x has to be the same as y over 10. This ratio of the height over the base has to be the same as the height over the base. Maybe I put in brackets here to remind myself what ratios was I comparing on the red triangle and the blue triangle. I was comparing the height over the base on both of them. Because I needed the height because that's where my y value was, and I needed the base because that's where my x value was. Now I could do the derivative with respect to time of this right here. I could also rearrange it. Maybe I want to get the y by itself. Maybe you got the 20 by itself. Then if I take the derivative with respect to time of this, and I move my x up so I could use my power rule, the derivative of y is dy dt. Bring the negative out in front, subtract 1 from the exponent, would give me negative 20 x to the negative 2, which I could write as x squared on the bottom. And looking at what do I need from my diagrams? Well, I was given dx dt. The only thing I need from my diagrams is my x, which is this value here. In the specific, it's not the 3, it's the 7. So a little bit easy to maybe make some mistakes here, okay? Because you might want to plug in the 3 because they gave you when x is 3. But we have to look at our specific diagram, and if I decide this is my x, because I was given that as dx dt, then the moment this is 3, that would be 7. So you have to look at your specifics and make sure you're plugging things in correctly. The answer ends up being negative 4.9 meters per second in the end. Okay, this is where we'll stop.